chemical reactions. There. I guess you could say this chemical reaction sort of starts pulling things together. And we're going to look at different types of chemical reactions. We're going to look at the theories behind chemical reactions. Try to get a handle on why they do what they do. Then we're going to look at a little thermochemistry and finish up with equilibrium. And that will be where we take off for next week's lab. It's not so much the Chatelier's lab is not so much a quantitative exercise as a qualitative. You just make observations, just like one of those previous ones we did. Signs of chemical change.
Okay.
Yeah. Now, Boyle's law and molar mass, those were quantitative. Osmosis and dialysis, that was semi-quant. Okay. So just this actually is a review probably for you at this point. Whenever you have we're trying to describe a process whereby reactants or old substances change into new substances. And that's a pretty broad definition, but chemistry is a broad subject. Now, the types of chemical reactions can be, they're more operationally defined. In other words, they say something about the reaction, but they don't say everything about the reaction. You can have a descriptive term for a reaction, and then you can turn around and find another descriptive term that does pretty well for a different aspect of the reaction. For instance, if we have what we classify as an oxidation reduction reaction, of course, that doesn't mean anything right now, but it can also be a combustion. So you can have more than one descriptive term for a reaction. And we're going to look at these in detail. So a combination reaction is simply where you have two elements. This example, calcium and sulfur are combined to make calcium sulfide. That's a combination. Then if you flip it around and you say calcium sulfide becomes calcium and sulfur, of course, by a different process, but the equation, the reaction description would be the same, only in reverse. That would be if this is a combination, then the opposite would be a decomposition. And to give a different example here for decomposition, copper 2 oxide makes copper and oxygen. A displacement reaction is where you have one element combined reacting with a compound, and the element replaces one of those members of the compound. So in this case, you get iron. Iron is displacing copper. So you get the copper metal here, and you get iron combined with sulfate. That's a single replacement or a displacement reaction. You can call it either one. This is also an example of an oxidation reduction reaction, which I haven't defined yet, but I will. Or you may already know if you've read ahead. Exchange reaction is where you get two compounds and they just swap dance partners. So a good example here is silver nitrate in aqueous solution, sodium chloride in aqueous solution, and the silver and the chlorine now combine. Silver from here, chlorine from there, to make silver chloride, which is a precipitate, and then sodium and nitrate are left over. And this is a description. This is a paint myself into a corner. molecular equation. That's what we call it. This is a molecular equation, but in reality, you know that an aqueous solution of these two is going to be silver ions and nitrate ions. This one's going to be sodium ions and chloride ions in solution. We write it this way for convenience and for simplifying the balancing process. But in reality, these will be separate ions in solution. Whereas this one is definitely a solid and it precipitates out. And these ions are left over. Sodium and nitrate are still in solution. They were in solution over here, they're in solution over here. So just as a teaser, the driving force for this reaction is the combination of silver and chlorine to make silver chloride. And those other ions, the nitrates and the sodium, are just spectators. But that is an exchange reaction or a double replacement. That's another name for it. And that is true, very often accompanied by precipitation. Not always, but often. Combustion reaction. The key to a combustion reaction is you have elemental oxygen as a reactant. So anytime you have oxygen here, always suspect a combustion reaction. And by the way, that's also an oxidation reduction reaction. Okay, so let's see if we learn anything from this. What type of reaction is this? You've got a compound producing simpler compound. Looks like a decomposition to me. A single replacement, no, because they're not two. There's only one reactant. There's only one reactant, so it can't be these two. It's not a combination because you don't have two things combined. So decomposition is the only. Now, when we showed you the examples, we had two elements combined to make a compound. Or a decomposition, we had a compound becoming two elements. But the key to a decomposition is a compound becomes multiple simpler compounds or elements. There you've got an element, but you have these compounds also as a product. Okay, let's see if we can classify each one of these as combination, decomposition, displacement, exchange, or combustion. All right, let's see, what do we have here? We have an element and a compound, and it looks like the magnesium swaps place with the hydrogen. So that would be a single replacement or a displacement reaction. Let's see if I put that in here. Yeah, displacement. How about the next one? That looks like a synthesis. You have these two coming together to make a single. Combination. Okay, another word for that is synthesis. Yeah. It can get confusing because it depends on what language you're speaking. And that's not good for the sciences. When you say something, everybody in the room who's trained in sciences should understand exactly what you mean. It's not ambiguous, it's not redundant. But science is, after all, a human endeavor, so you can expect things like that. How about this other one? Let's see, ammonia and oxygen. That looks to me like a combustion. You know ammonia could burn. Yep. It will do that and makes nitrogen monoxide and water. Now, since we haven't defined oxidation reduction, that's not one of the choices. But this is an oxidation reduction reaction. This one is also an oxidation reduction. And I know that because the combustion is always oxidation reduction. And whenever you have an element on one side and it's in a compound on the other side, you have an oxidation reduction. That's a rule of thumb. But we can prove it once I give you the proper definition and the rules to go by. Okay. An oxidation reduction reaction, which we abbreviate redox. In other words, it's not oxred, that just doesn't sound right. So oxidation reductions are redox reactions, and they're reactions in which electrons are transferred. That's the only condition. In the reaction, electrons are transferred from one element to another. If it's a non-redox reaction, all you have to do is show that electrons were not transferred. And here is one of your rules of thumb, right, that I mentioned earlier. If the element is free on one side and then a compound on the other side, it's a redox reaction, without question. Or if it's an element on the product side and it came from a compound on the other side, on the reactant side, that's also a redox. And very often you get swapping places. All right. So what we need is a way for redox reactions. What we need is a way to track our electrons, know where they're going. There's a bookkeeping scheme, and it employs oxidation states, sometimes oxidation numbers, which you'll see them called. And all it does is it assigns a theoretical charge to each of the elements in the reactants and products. Now, if they're all ionic in nature, ionic compounds, then they will be charged. That's true. But you can use oxidation states in covalent compounds to help track the flow of electrons. And just realizing that in those types of compounds, they do not have charges. For instance, the difference between carbon in this compound and carbon in that compound. They're both covalently bound compounds, but we can assign an oxidation number for this carbon and that carbon. This one would be +4, and this one would be -4. Right? So they have different oxidation numbers, but we know they're not charged because they are covalent compounds. It's a bookkeeping scheme. And it's one of several that are available. It's just that this one is the easiest to learn, and it satisfies the requirements we need for redox reactions. Okay, let's see. Here are the rules. If you have a reaction, or if you have a compound, it's not in a reaction, and you want to know what is its oxidation number, its oxidation state, use these rules. If it's an element in its, if it's an element, then the oxidation state is 0. In other words, it's not positive, it's not negative. And that's true for all elements in their standard state, standard temperature and pressure state. So for all of the metals, except for maybe a couple of them, they'll just be the single element symbol. And that will be like calcium, for instance. If we just write that, then its oxidation state would be 0. And we put the oxidation number in the same place we would put the charge. If it's oxygen, though, or one of the diatomics, it would have to be like that to be a 0. Or nitrogen, dinitrogen, or hydrogen. It would have to be like that to be a 0. That's the first rule. If you have a monatomic ion, For instance, if you have sodium chloride compound, we know that this one is going to be the cation. So its oxidation number is +1, and the oxidation number for chlorine is -1. Okay? Or if you have the ion separate, right? If we write the equation in such a way that we've pulled out the ions, separated them for convenience, calculation purposes, then if it's got a charge on it, that's its oxidation number. Oxidation numbers for the alkali metals are all +1. So anybody in that first column is a +1 if it's in a compound. Okay? If it's a free element, it's 0, according to that rule. Alkaline earths are all +2. Okay? There should be another one in there. I'm going to leave it at that for now. But if we need any more rules, I'll give it to you. Well, let's move to hydrogen. Hydrogen in most compounds is a +1. So if we were saying water, then we would give hydrogen a +1 oxidation number. And oxygen would be -2. Which is the next rule. So oxygen in all compounds, with one exception, are always -2. If you have a compound where you've got two oxygens bound together like this, and then you got something else attached to them, that's a peroxide. Peroxides give oxygen a -1. But all other times, oxygen is -2. So this as a group is a -2. Okay. In what they mean by binary molecular compounds are covalent compounds, right? As opposed to binary ionic compounds, binary molecular compounds. We put the more electronegative element is assigned a negative oxidation number. So if you have, let me try to think of an example. How about this one? Laughing gas. Right, the more electronegative one is oxygen, right? It's to the right of nitrogen. So it's going to be the negative one, and you're sure to give it a -2. That means the nitrogen has to balance it. And that's rule number 7. You have to balance all the oxidation numbers. If there's no charge on the species, then they have to be equal to 0. If it's a polyatomic ion, then you add them all together and they have to add up to the charge on the ion. Okay, so in this case, the negative is in the anion position. The nitrogen is in the cation position. And that means each nitrogen has to be +1. Right? We don't know what nitrogen is, so we have to work with what the rules say oxygen is. Oxygen's -2, so nitrogen has to be a +1. If we had a different compound out of those same two elements, like that one, nitrogen dioxide, this would still be -2, which means a total of -4 for the two, that means this nitrogen has to be +4 because the total has to add up to 0, has to balance. And we'll do some examples where we have polyatomic ions. Okay. Okay, so we're going to do it right now. And deduce oxidation numbers for elements that are not included in the rule set. How about this one? Potassium dichromate. Okay, what do we know? We know that the rule says that alkali metals are all +1, right? And oxygens are always -2. So we have a contribution of +2 out of the potassiums, and we have a contribution of -14 out of the oxygens. Okay, so +2 and a -14 is -12. That means that the leftover, this chromium, has to balance that -12 with a +12. So these two together have to be a +12. That means each one of them has to be a +6. Okay? And let's see. There you go. Conformation. Next one is a polyatomic ion, a carbonate. I got to remember to write bigger because it shows up better on the video. In fact, I need a darker. Let me get another. Let me get a new marker. I get weak like that sometimes. At least when I'm processing the video, I can't even see them. What was it? CH203 2-. Yeah, that's better. But that'll show up. Okay, so we know that this oxygen is a -2, which means -6 total, right? So -6 is from this oxygen. But there's already a -2 reserved for the charge. So we only need to balance a -4. So that means this has to be a +4. And then you can check yourself. So, yeah, okay. We've got -6 from the oxygens and a +4 from the carbon gives us the charge on the polyatomic ion. It's kind of like making change the old-fashioned way. Do they teach that anymore? Where you have somebody buy something and it may, they owe you that much, but they give you a $5 bill. Right? So you take their money and you start reaching in the cash register and start counting it back to them. Say $1.25, a nickel, and then 2 dimes or a quarter. Let's make it a quarter. Give them a quarter. So you're saying, no, I'm sorry. You give them 3 quarters. That makes, so you start counting it back. Say $1.25, $1.50, $1.75, $2. Then you reach in there and grab the dollars out. $3, $4, and $5. And you're done. That's the way we used to make change. And you never make a mistake. Now the cash register tells you how much change to give, and you just give it to them. And maybe it's right, maybe it's not. Right? But when you count it back to them like that, the old-fashioned way, when we had mechanical cash registers, right, where you had to push 3 or 4 buttons at the same time. You remember those? See them on old movies. Well, that's kind of like what I'm doing here with the carbonate ion. Right? I'm saying, all right, it's already paid me 2 minuses, and I got 6 minuses, so that means I only have to balance 4 of them. Well, I don't know if that made any sense or not. I'm just reminiscing. Oops, won't do that yet. Okay, so manganese dioxide. What do we know? We know the rules tell us that is -2. Times 2 is -4. So -4 is the total negative that we have to balance with positives. That means there's only one of these, so it has to be a +4. Okay? It's really pretty simple. If you haven't figured out by now, scientists, chemists, scientists in general are pretty simple-minded people. We don't like complexity unless we absolutely have to. Okay, how about PCl5? Sometimes you get, now we didn't talk about halogens, did we? Was that one of the rules? I don't remember seeing halogens in there. Halogens, if you have a compound with a halogen in it, then it's a good place to start. And halogens are going to be -1. So that means -5 total. That means +5 for that phosphorus. And if you look at, well, that periodic table and I think one of the periodic tables I've given you has a list in the box, right? In the box down this side, it has numbers, pluses and minuses. Those are possible oxidation numbers for that element. The first one is going to be the one that's assigned to the ion of that element if it's in an ionic compound. So all of the halogens are going to start with a -1. Every one of them will have -1 first. And then if it has several of them below it, those are oxidation states that could exist for that particular element. So fluorine is always -1. It's never anything else. But chlorine, I can see it from here. It's got 1, 2, 3, 4. It's got 5 possibilities. Right, so how do you tell? Well, it depends on what it's combined with. Right, if I had chlorine and oxygen and say hydrogen, right? Fluoric acid, then I would start with what I know. This one's +1, this one's -2. And chlorine would be the one that is variable. So this one would be what, -6 total? 3 times -2 is -6. This would be +1. So put them together and it's supposed to be neutral. So you need balance -5. So this would be +5. And if you look on the in your periodic table, +5 should be a possibility for chlorine. And that's not a charge, that's an oxidation number. Okay, let's get back to this one. Okay, so phosphorus is +5, chlorine's -1. And we chose chlorine as -1 here because where do you start? Phosphorus doesn't have a fixed oxidation number. Chlorine, however, is more electronegative, so we're going to start with that one as -1. If we don't start with -1 as chlorine, then just throw up your hands and walk away. You're stuck. So since it's a bookkeeping scheme, and we can make the rules, well, somebody made the rules, but you have to do something or you can't go anywhere. And that's no way to bookkeep. This one we do the same thing, only we start with fluorine as -1. And then we calculate sulfur to be +4. All right. So if we want to identify a reaction as redox, we need to know the oxidation numbers for each of the elements on the reactant side and the product side and compare them. Does this element oxidation number change from this side to this side? If it doesn't, then go to the next element. If you don't find any elements that change their oxidation numbers in the process of the reaction, then you don't have a redox reaction. All you need is one to change from one side to the other, and you have a redox reaction. Well, actually, there's another rule. When you have a redox reaction, if say on the reactant side, say we have A and B yields C and D. Well, actually, let's do it this way. We need a compound. Let's see, AB plus CD. Let's make it a double replacement. So this one would swap places with A. So CB plus AD. Okay, if that's the case, if A on this side is, say, just make something up, say it's +1, and on this side it's a +2. Well, it had to lose an electron to get there, right? Because you can only change oxidation states the same way you would change a charge, by electron movement. So if this one lost an electron from here to here, and then somebody else has got to gain the electron. You can't have a reduction without an oxidation. They always come in pairs. So if you find that the oxidation number changes for one of them, then there's got to be another one in there that goes the other direction. This one became more positive. The other one has to become more negative because it received the electron. Okay, here's an example. Calcium and chlorine. Okay. Right there, elements, so they're zeros. But when you put them in the compound, chlorine is -1 and calcium is +2. That's a no-brainer because of the rules say that the alkaline earths are always +2. So the chlorine has to be a -1. No other possibility. And we notice that who did what? Right? Calcium became +2, so it lost 2 electrons. Chlorine became a -1 for each chlorine. So that means the whole group, the 2 chlorines together, gained 2 electrons. So each chlorine gained 1 electron. So you lost 1 electron, you lost 2 electrons with calcium, chlorine picked them both up. Now they're actually ions in that compound. And this just illustrates that it's an extremely reactive process. If you have calcium metal and chlorine gas, it gives off a lot of heat. Okay. How about assigning an oxidation number for sulfur? Right, so we know that hydrogens are +1s. Oxygens are -2. So this is going to be a +2 for the hydrogens and a -8 for the oxygens. So together, that's a -6, right? That means this sulfur has to balance that -6 with just 1 atom. So this 1 has to be +6. Okay? So, might as well make it official. It's kind of hard to see that one, isn't it? Need to edit that one, put a box around it, be more obvious. Okay, so for redox reactions, I alluded to these before. When you have, I think I've got a slide in there for this, but I'm going to put it up here now. This is your acronym, right? Oxidation is loss. And reduction is gain. So whenever you have, when something has lost one or more electrons, it is said to be oxidized. It's undergone oxidation. So that means something else had to gain that electron or more electrons. And reduction is gain. So when you think in those terms, oxidation and reduction are joined at the hip. You can't have one without the other. If you lose an electron, somebody's got to gain it. Now, let's see. Let me look ahead. Oh, there's the oil rig. There you go. No, we need an example. Let's use our calcium and chlorine example that we had previously. So there's calcium and chlorine yields calcium chloride. There we go. So if we start off with 0 here and 0 there, and by the way, that 0 is for each chlorine. Then on this side, we have 2 plus and we have 1 minus. All right, so what's happened? I like to draw these connectors. What happened here? You had to lose electrons, right? So we have a loss of 2 electrons per calcium. That means here we had to gain 1 electron per chlorine. Times 2 equals 2 electrons. Okay? These numbers, since there's only 1, 2 electrons, you have to gain the same number of electrons that you lost. That has to balance, right? We're not dealing with electrostatics here. Excuse me. We are in a certain sense, but we're not accumulating charges like a Van de Graaff generator. You have to balance. So if you lose 2, you have to gain 2 somewhere else. This is oxidation, and this is reduction. Well, since they come in pairs, they always come in pairs, then what caused that oxidation? This is an oxidizing agent because it caused the oxidation of calcium. And this is the reducing agent. Because it caused the reduction of chlorine. Okay, just by way of definition. All right. So the oxidizing agent has to gain electrons, and the reducing agent has to lose electrons. That's what we said here. Whatever causes the oxidation or loss of electrons has to gain the electrons. So the oxidizing agent has to gain those 2 electrons. Let's see. Yeah, that's nothing new. All right, this is what the authors of your book think is helpful. I don't know if it is or not. So when you have oxidation, the oxidation number increases. Oxidation is loss. So that makes sense. The number has to get larger or more positive because you're losing electrons. And if you're gaining electrons, the oxidation number of that element gets more negative. That's all this thing is showing you. Oxidation goes this way, reduction goes that way. Okay, so let's identify what is oxidized and what acts as the reducing agent. So let's see. Start with the easy ones. 0 and 0. Okay, so notice that the nitrate doesn't change. It's the same on both sides. Right? So we don't have to deal with the nitrate at all. All we have to do is look at the metals. So what is the charge on this one? Well, let's see. Nitrate is a -1, so this silver has to be a +1. Nitrate is a -1, and we got 2 of them, so this one has to be a +2. Okay. All right. So what is oxidized? What loses electrons? Copper. Copper loses electrons. So that means the reducing agent is silver or silver nitrate. So copper is oxidized, yes, and silver nitrate is the reducing agent. Technically speaking, copper is oxidized. Yeah, silver gains electrons, so it is the oxidizing agent. Okay. Excuse me. Copper is oxidized. And what acts as the reducing agent? Well, silver is reduced, so copper is also the reducing agent, isn't it? What's oxidized? What is oxidized? Copper is oxidized. Right? So it's either this one or this one. And it says this one is silver nitrate is the reducing agent. Silver nitrate's the reducing agent. Oh, the top one's red. Excuse me. Yeah, okay. I'm colorblind. Yeah. All right. So copper's both of them. Did I confuse anybody? Okay. Confused myself. Which of these are oxidation reduction reactions? And then identify the oxidizing agent, the reducing agent. All right, we can use rule of thumb also, right, to find out immediately which one's oxidation reduction. We have an element here, it's in a compound there. That's an oxidation reduction. We have a copper element here in a compound, and it's elemental over here. That one is oxidation reduction. This one, there's no clear indicator, no rule of thumb for that one. So we need to determine what are the oxidation states for each one. Well, oxygens are all -2. -2. -2. Hydrogens are +1. +1. So yeah, it looks to me like that one's not. Because if all of these, if chromium changes its oxidation state, where are the electrons going? There's nowhere for them to go. Now, sometimes you do get oxygens and hydrogens changing their states. But in this case, no, they're all constant across it. That's not oxidation reduction. We can confirm it, right? This is 4 times -2 is -8 for that oxygen. But we have to hold out 2 of them for the negative charge. Right? So this chromium bleeds +6. We do the same thing on this side. We have a 7 times -2 is -14, but we hold out 2 for that 2 minus. That means we only have to balance a -12 with a +12, but we have 2 of them, so it's a +6. So that confirms it. The second one is not oxidation reduction. Okay, then we have to say which is the oxidizing agent and which is the reducing agent? Well, zinc is oxidized. It goes from 0 to +2. So the oxidizing agent will be hydrogen chloride. The reducing agent would be the zinc. Okay. Zinc is the reducing agent, HCl is the oxidizing agent. Then for this one, this is an unusual one. Notice that we've got copper over here is +1, right? Chlorine's -1, copper's a +1. So we're going from +1 to what? 0 here and -2. Oh, see, +2 here. So how does that happen? Well, you've got two compounds. Right? It's like writing that, and that produces like that. So one of them goes this direction and the other one goes the other direction. It's called disproportionation reaction. So this one starts off at a +1 and that's +1. But one of them goes to a 0 and the other one goes to a +2. So the one that goes, just arbitrarily pick this one goes, loses 1 electron per copper. And this one gains 1 electron per copper. Okay, so what does that mean? Well, the oxidizing agent is the one that's reduced. And the reducing agent is the one that's oxidized. So they're both. It's my father used to have an expression when he was disgusted with the stupidity of somebody. He says, that guy doesn't know the difference between an adverb and a horse. It's obvious. One leg is both the same. One leg is both the same. He was a teacher too. Okay, so now we're going to look at theories behind reactions. And this is the collision theory. Like I said before, it's very simple. First of all, in order to have a chemical reaction, you've got to have the reactions collide with one another. They got to meet. If they don't meet, there's no reaction. So that's the first condition. You have to have molecular collisions. Then they have to collide with sufficient energy and activation energy to start the process. If you don't have enough energy, they just kind of come by and say, how you doing? And go away. And then it's also important that they're oriented properly, because that activation energy is required to break a bond so that you can reform the bonds that you need for your products. So if the reaction sites for the breaking and forming of bonds are on this side of the molecule and they come together like that, doesn't matter how much energy they have, no reaction. So those are three essential conditions in the collision theory. Right, what I said. They have to collide. They have to have enough energy, kinetic energy, in order to initially break bonds and start to form new ones. They go through an activated complex state. And I'm not sure, do I have a picture of that diagram of that one? Graph with a hump on it. Okay, good. So I don't have to draw it. And then orientation is essential. All right, so this is your artist idea of explanation. For this, in this case, we have proper orientation. and we have enough energy, and they collided. And what we get is nitrogen and oxygen forming, coming out with the existing bond here. But this bond is broken and transferred to that carbon monoxide to make carbon dioxide. So they're oriented properly to get that connection and with sufficient energy. These others don't have the proper orientation. They will not produce a reaction. At least not the one you desire. I guess we could get really complicated. If they come together wrong, then you could produce a different product. And then as a synthetic chemist, you'd have to separate the products. But sometimes it's fun and sometimes it's not. It's best if your products are all one type, the one you want. Okay, what are the three factors necessary for chemical reaction? I'll just give them to you. Collisions, activation energy, proper orientation. This qualifier, low activation energy, you're more likely to get a reaction if it doesn't require a lot of energy to get the thing started. All right, so the reaction can proceed at a lower temperature. That's what we're saying. Lower activation, lower temperature, because temperature is what? Temperature is the average of the kinetic energy of all the molecules in your container. So low temperature means low activation energy. And low activation energy means that the reaction is going to proceed with more of the collisions. Okay. So what do we mean by exothermic? When we talk about reactions, sometimes it's instructive to draw a picture. This is your system. And this is your surroundings. Have I ever drawn this one before? No? Okay. Surroundings. There we go. So everything that we describe is in terms of the system. So if something happens in the system and the surroundings get warmer, then we've transferred heat out. Let's see, the proper abbreviation for that, or letter for that, is a small q. So heat transferred out is exothermic. Out, heat, exo, heat. If, however, the reaction absorbs energy from its surroundings, then we have endothermic. Okay? If we put a number on this, like so many joules per mole, so many joules for that reaction, then the number is going to be in this reference also. Right? Exothermic means heat is leaving the system. That means it's negative. And if heat is being added to the system for an endothermic reaction, it's positive. Okay. We probably won't have to do that because I don't think in this course we do a lot of those extensive calculations, but it can be done. If you're ever presented with that in the future, then you won't be completely at a loss. Impress your friends at parties. Okay. When we write the reaction, say we have, we've got reactants leading to products. Sometimes it's instructive, and particularly for our Le Chatelier's lab, it's instructive to consider the energy or the heat component as a reactant or a product. So if it's exothermic, that means the energy that was contained somewhere in here is now over here. Right? It's being released as heat. So if we do it that way, then we can use this later when we start talking about Le Chatelier. I'll come back to this. But if it's endothermic, naturally, the heat component will be on this side. Heat's going in here and it's stored in the products. So we had to add energy to the system to end up over here. If you've ever used those hot or cold packs that hospitals keep, they've got a little a container of some solid chemical and then a bag of water around it. And all you have to do is break it, mix it together, and the heat of solution, which is a type of exothermic or endothermic reaction, will either make the bag hot or cold. So if it's endothermic, you can feel it drawing heat from your hand. If it's exothermic, you can feel it adding heat to your hand. Okay. Oh, there it is. Okay, so in reaction terms, if this is the progress of the reaction from left to right, this is where it starts, and then after a certain amount of time, you end up over here. These are the reactants, and the energy of the reactants is here, combined total energy of the reactants. And over here is combined total energy of the products. So that being the case, you have actually started off with more energy that you ended up with. Where did the energy go? You can't create it. You can't destroy energy. It's got to go somewhere. It's exothermic. You started high, you end up low, it gives off heat. Oops. So the heat is here, and it will have a negative sign. And the amount of energy it took to get things started is this difference here. It goes up here to an activated complex state. You add energy into it, and then once it gets exactly the energy it needs plus a hair more, goes down the other side. And if this is nitroglycerin, well, that's not a good example because nitroglycerin decomposes. You have to have binary explosive. You have two things. Make me a combustion, say octane and oxygen in your cylinders of your engine. They have a certain amount of energy, right? And you add energy to get them started. Where does that energy come from? Spark plug. Zap it with electricity. It goes up here and down that way. It makes, ideally, carbon dioxide and water out of your octane and oxygen. It gives off heat. And then your engine extracts that heat and turns it into motion. Some of it. Ranging from 15 to 30%. Really high efficiency engines will get you 30% recovery of the heat. And the rest of it, you just have to blow off into the atmosphere. Or into the cabin if it's the middle of winter. Okay, so that's an exothermic reaction. Endothermic reactions store energy in the products. Right? Photosynthesis is a good example. So you got energy coming in from the sun in the form of sunlight, and the plant captures that energy and builds it into molecules. Right? The first molecules it produces are usually 3 carbon compounds. And then it builds from there. But the energy is stored in the structures of the compound. And this is what it would look like. Right? So carbon dioxide and water in the atmosphere is what the plants take in. It adds energy from sunlight. And now the energy is stored in carbohydrates and fats and proteins, other stuff, nucleic acids, whatever it needs to build a cell. So this is an endothermic process. Okay? And the energy absorbed is the difference here between what it was and what it is now. The activation energy is what the reactant started at and what was required to get the reaction to go. So for endothermic reactions, the activation energy is huge from here to here. Okay, which one of these is correct? During an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. That's endothermic. During an endothermic reaction, the average energy of the products is lower than the average energy of the reactants. Wrong. C, during an exothermic reaction, the average energy of the products is lower than that of the reactants. C is your answer. It's supposed to be red. Okay. So at this point, we've only talked about before and after. Well, we sort of talked about activation energy, which is in between. But if we're interested in endothermic or exothermic reactions, it doesn't matter how they got there. They could go through several steps. And in fact, in photosynthetic processes in biochemistry, you go through multiple steps to get where you go. Like start off with carbon dioxide and water, you make this little compound and you change it and you add something else. Go through 100 different steps to get to, say, cellulose for a tree. As far as the energy expenditure or the energy storage, or the energy you get back, whatever the case may be, it doesn't matter how you got there. That's thermodynamics. In other words, it just matters where you started, where you end up. But it's also useful to know sometimes how long does it take you to get there? Because you can have a thermodynamically unstable molecule. In other words, it prefers to be decomposed. Right? Say, good example is diamond. Diamond in an oxygen atmosphere is unstable. Eventually, it will decompose into carbon dioxide. But the key is it takes millions of years to get there. And so there's two different ways of looking at that problem. The thermodynamic way says, yeah, diamond is unstable. It's going to go to the carbon dioxide. But the reaction rate or kinetics of that process takes a long time. All right, so that's what we mean here. Chemical reaction rate is referencing kinetics. The rate at which a reaction proceeds. Reactants are consumed and products are produced over a given period of time. Now, what affects the reaction rate? Well, the physical nature of the reactants, right? How finely divided are they, especially for solids? If you have a perfect example is coal dust explosions in a mine. That's why the rules say that you have to keep these shafts ventilated to drive out the dust. Because if you collect a certain amount of dust in an oxygen atmosphere, all you need is a little spark and it will blow. In other words, the reaction rate is very fast because the surface area is extremely large for the coal dust particles in an oxygen atmosphere. And that's where the reaction occurs, at the surface of the particle. If you had a large chunk of coal, right, you could stand there with a lighter for 15 or 20 minutes and eventually get it to light. Maybe not that long, but it would take a lot longer and then it would just burn slowly. But you divide it into very small particles and you get an explosion or potential for an explosion. Reactant concentrations. So if you have actually any type of reaction environment, you can have gases with high concentrations of say an explosive compound in the atmosphere, after it reaches a certain concentration, then all you need is a spark and it'll blow. So, or you could have solutions, right? And the rate will increase as you increase the amount of reactants in solution, concentration. That has an impact on reaction rates. Temperature. As a general rule, increasing the temperature increases the reaction rate. It's not always the case, but for most reactions, you increase the temperature, more of your reactants have enough energy to exceed the activation energy. That's the key here. And do you have any catalysts in there? A catalyst always increases the reaction rate. So if you have a catalyst, it will, actually the catalyst works by giving your reaction a different pathway. And the pathway for a catalyst is always lower activation energy. That's how catalysts work. You gotta go?
Yeah, I'm sorry.
Okay. Oh, we're good, because we don't have a lab today. Okay. So, what's the physical nature of the reactants? Right? Solid, liquid, or gas? Or for solids, particle size? If all of the reactants are the same physical state, like all liquids, all gases, or all solids, the reaction is generally faster between liquid states than it is for solid states. That's just a rule of thumb. And the reaction for gaseous state is faster than either one of these, simply because you have more potential for contact with a gas than you do with two liquids or with two solids. I mentioned this one earlier. If the particle size is very small, the reaction rate will be higher. They can be so fast that you can produce an explosion. A coal mine dust explosion. In fact, where was it? Kansas or Oklahoma? This has been several decades ago. They had this one place with a rail line where they collected grain, and they stored them in these huge silos until the train came through and they sold them, and the train carried off the grain. Well, those silos were not maintained very well for accumulated dust. And the dust from grain is combustible. Right? All you need is a spark in an oxygen atmosphere, and that's what they got. Those things blew up. And in addition to that is those silos are sealed. Right? So one thing that every Islamic terrorist knows is if you take a slow reaction and put it in a container and confine it, it'll build up pressure until it finally exceeds the physical limits of the container, and then it'll blow. So that's what the Tsarnaev brothers did at the Boston Marathon. They put gunpowder and something else in a pressure cooker and set it off in the cooker, and it was a slow reaction, but it built up enough pressure, and then bam, it went off. So yeah, you can get dust explosions. Reactant concentrations, more molecules of the reactant present in the reaction mixture, thus you have more collisions. So we're going back to the collision theory to influence the reaction rate. The more collisions you have, the higher the probability you will have a reaction. So the reaction rate should increase, even if the temperature remains constant. And then the temperature, of course, supplies enough kinetic energy to exceed the activation energy. That's the key to reaction temperature. Now, a catalyst is any introduced element or compound into a reaction mixture that causes the reaction to increase its rate, but the catalyst is not consumed in the reaction. It's intimately involved in the new reaction, but it's not consumed. In other words, if it comes in one side and goes out the other, it's a catalyst. And it always increases the reaction rate compared to the uncatalyzed. Now, enzymes, I heard about enzymes. They are biochemical catalysts. They speed up biochemical reactions. But they're special. Enzymes are not, strictly speaking, like inorganic catalysts. Inorganic catalysts, they do one thing. They speed up the reaction in both directions, actually, forward and backwards. Enzymes are a little more sophisticated than that. They do speed up a reaction, but they also control the reaction. So an enzyme has to be activated before it will cause the catalytic process to occur. So that means the cell can deactivate an enzyme if it doesn't want that reaction to occur. It can respond to some other stimulus. And then when it wants the enzyme to promote the reaction, it activates the enzyme, and there you go. And most of them, not all, but most enzymes only work in one direction. So it controls the reaction in terms of speed and on-off switch and direction. It only goes one way. So that means if you want the reaction to go back the other way, you need a different enzyme. So, but to make a long story short, enzymes are more sophisticated than inorganic catalysts. Like the Haber-Bosch process, I've used this one before, where you have nitrogen combined with hydrogen to make ammonia. Let's see, 3, 2, there. This process is not economically feasible unless you use a catalyst. So Haber came up with a catalyst who just finely divided iron. And it caused the reaction rate to proceed faster. And he also increased the temperature, high temperature. So he added heat to it. The problem with that is this is an exothermic reaction. So if we put our Q on this side, then what happens when you add heat to this? Well, we haven't talked about it yet, but Le Chatelier says if you add heat, it's going to force it back that direction. So that's why he needed a catalyst to increase the rate of forward and reverse. Now he gets more of this, and all he has to do is cycle it through a cooling unit, and the boiling point of nitrogen and hydrogen are very, very, very low temperature. So all I had to do is cool it a little bit, and the ammonia drops out. And then he takes the gases off of that, sends it back through the reactor. And you do that 5 or 6 times, and you get 15 or 20% efficiency, and now you can make money. Or explosives, whatever the case may be. Okay, so this is what a catalyst would look like. The uncatalyzed reaction is the higher activation energy. And the catalyzed reaction is the lower activation energy. So when you lower the activation energy, more of your molecules now have sufficient kinetic energy to react. And that's why the reaction rate with a catalyst is faster, because you effectively increase the number of reacting species in your mixture at a given temperature. Okay, so the function of catalyst in the chemical reaction is to increase the rate of the reaction by decreasing the activation energy. We're not going to talk about different types, homogeneous or heterogeneous catalysts. Is that not part of our discussion? I guess that's, no, that would be asking too much. But the phase of the catalyst can be, sky's the limit. If your reactants are all liquid and your catalyst is, or gases, like the Haber process, they're all gases, but your catalyst is a solid, that's known as a heterogeneous catalyst. It's not in the same phase as the reactants. If you want to decompose hydrogen peroxide and put a little soap and food coloring in it and make a colored fountain, right? You put potassium iodide solution here and your bottle of hydrogen peroxide with a little soap and color, food coloring, and you dump it in there. That's a homogeneous catalyst because it's in the same phase as the reactant. Okay, equilibrium. Equilibrium is a term. In chemistry, we use it to describe the appearance in a chemical reaction of the appearance of static conditions. In other words, you get reactants and products, and at some point, the concentration of reactants and products, wherever that may be, stabilizes, doesn't change anymore. So you may start off with all reactants, no products, and then you'll make products, but at some point, it will appear as if you've got this much reactant left, this much product, and it doesn't change. That's an equilibrium state, a chemical equilibrium, where the concentrations appear to not change. They don't have to be exactly equal either. You can have an equilibrium where you have just a little bit of product produced and mostly reactant still. Or you can have very little reactant left and lots of product. Okay, so what's happening? Well, here's an example where you have the forward reaction here is hydrogen and iodine yields hydrogen iodide. So if you start off with hydrogen and iodine only, then it's going to produce hydrogen iodide, and the reactants in this light blue line are actually going to decrease over time. And then you're producing hydrogen iodide, it increases in concentration until you reach a point where this forward reaction is balanced by that reverse reaction. Notice this is the reverse of that one. Sometimes we write it like this. Actually, it's more convenient to do it this way, with a double barbed arrow. That says this reaction goes both directions. And at the point where the forward reaction rate equals the reverse reaction rate, you have equilibrium. Sometimes we do, let's see, if we have an R here and an R to the -1, this is the forward rate and that's the reverse rate. So the moral of this story is it looks like there's no change occurring. You reach a point where you have a certain amount of reactant left and a certain amount of product produced. That's at the macroscopic level. The microscopic level, underneath, these forward and reverse reactions are occurring at furious paces. I mean, the activity is unbelievably fast, but there is a balance between the rates. Let's see. This one was reaction rates. So the rate of the forward reaction is actually decreasing. I misspoke earlier. This is reaction rate decreases, this reaction rate increases for that one versus this one. When you look at the concentration of the reactants and products, the reactants are decreasing as you produce products. Right? And at some point, it appears that their concentrations are stable and don't change. Okay. What's a reversible chemical reaction? It just says that the reverse reaction can occur. If you write the reaction to go this way, you can also write it to go the other direction. At some level, all reactions are reversible. They can go in either direction on the microscopic level. Now, if the rate of, say, let's go forward with a reaction. If the rate of the reverse reaction is so slow that you essentially convert all of the reactant to product, or the measurement of the remaining reactant is so low, it's almost undetectable. At that point, we may say it's irreversible. It goes essentially to completion. So that's why I put it in quotes. Excuse me. That's why I put it in quotes. Because at some level, all reactions are reversible. But we can use an operational definition here to say, all right, if it goes so far to the right that you've had practically nothing left in reactants, we call it irreversible. Okay, a state of blank is reached when the concentrations of all reactants and products remain constant. And a blank is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. So a state of chemical equilibrium is reached when the concentrations of all the reactants and products remain constant, and a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur simultaneously. Here we go. Okay. So now we're going to get into, we're leading into Le Chatelier's principle. When you see this reaction, which is written in only the forward direction, and actually it would have been better to write it this way, based upon our previous discussion. Let's say this mixture now is at equilibrium. Doesn't matter how it got there. Maybe you started off with all reactants and you make some products and now it's at equilibrium. Then, what would you expect to happen if you add more water to the flask? Well, now you have more water to react with any carbon monoxide that's left, right? So you're going to get some of that water consumed and some of the remaining carbon monoxide consumed and make more of these until the balance is reestablished. And you get the rates, once again, are forward, reverse, equal rates. How about if we add more hydrogen? Well, now the reverse reaction is favored because you have more hydrogen in there to react with some carbon dioxide. And then you're going to make some more of this until you reestablish equilibrium. That, in a nutshell, is Le Chatelier's principle. We start off at equilibrium, which is a happy medium, and then we disturb it. We do something to upset the equilibrium. In this case, we're adding reactant or we're adding product to do it. We'll come back to Le Chatelier in a minute. The equilibrium constant is a way of quantifying that situation where you're at equilibrium. It's a numerical value. And as long as the temperature remains constant for a given reaction, the constant is constant. If you change the temperature, then you have a different constant. Right, so how do we write it? I don't like it that way. I like it this way, where you have a little a and a big A. So there's your coefficient. And then a little b and a big B. And now you have a little c and a big C and a little d and a big D. Still, I'm still picking it up. Okay, now if you write the equilibrium constant, it's the concentration of this reactant, and we use a square bracket. Square brackets mean equilibrium. So the equilibrium concentration of C raised to the coefficient power times the equilibrium concentration of D raised to its power. That's in the numerator. So the product side always forms the numerator, and the denominator is always formed from the reactant side. Okay. That is also known as the law of mass action. So in general terms, that's true. Let's see. I don't want to steal my own thunder. That's why I'm looking ahead. Yeah. If all of these are either gases or solutions, then you keep all of them. If that's a gas, 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 or a gas, aqueous, aqueous, gas, whatever the case may be, as long as it's a bona fide concentration. So gases can be concentrated, aqueous solutions can be concentrated. If it's a solid or a pure liquid, then that term drops out. You don't keep it because solids don't change concentration. Pure liquids don't change concentration. Okay. For instance, if we have hydrogen gas reacting with oxygen gas to produce, let's see, about to go off the edge here, produce water, that's a pure liquid. And this would be at standard temperature and pressure. So at 25 degrees, this is what you get. If you're in the bell of a rocket engine, right, that'll be a gas too. But under these circumstances, if we write the K, well, we get a balance at first, right? So we got 2 oxygens here, we need 2 there. Now we need 4 hydrogens. So now we would write the K in terms of, well, there's nothing up there because it's a liquid, pure liquid. So we'd only have the denominator. So we'd have the hydrogen here squared and the oxygen to the first power. Okay. All right. Let's move on. Square brackets are always used for equilibrium. If we have a non-equilibrium calculation, say we're starting off with a given concentration of this reactant, that product, but it's not an equilibrium yet, then you can still do the calculation, but you would use parentheses instead. Just to distinguish between equilibrium and non-equilibrium situation. Now, if you used the current status, not equilibrium, then you're not calculating a K. You're calculating a Q, which means reaction quotient. And this is useful, but I don't think in this class we're going to get it that far. I'm just throwing that out there so you won't be blindsided if you ever see it again. We've already said this stuff. Where do you put the products? Where do you put the reactants? And the coefficient, the units of the coefficient are never reported. Right? You may have molar concentrations for each one, but you raise one to a power and you raise this one to a different power. You can get really complicated really fast with the units of measure. So by convention, we don't report the units for equilibrium constants. We just have to be real careful how we calculate them. And if you ever pick up a reference manual and it lists equilibrium constants for different reactions, it will never give you units. What it will do is at the top or the bottom, it'll say derived from molarities, or derived from, if they're all gases, partial pressures. Those are the two most common, molarities, partial pressures. And then you just have to be real careful about your calculations and you'll come out all right. Oh, here it is. So pure liquids and solids are never included in the equilibrium expression. They can be viewed as sort of buried in the K value if you want. Otherwise, just ignore them. Okay. When the temperature changes, the value of K will change. So if it goes up, well, if the forward reaction is exothermic, in other words, that puts Q on this side. If Q is over on this side, exothermic, then the equilibrium constant decreases as the temperature increases. Because if you add more of this, what happens to the reaction? It goes back that way. That decreases the concentrations of the products and decreases the value of K. Okay? Should I say that again? Okay. If we have reactants over here and products over here, then your K expression then would be B over A. Okay? And the heat term is not part of the equilibrium, but it does have an impact. And the way it has an impact is if this increases in temperature, you add more of that, then by adding this side, you drive the reaction backwards. That decreases this one and increases this one. So if this one increases, this one decreases, K goes down. Okay. So the other way, if it's an endothermic reaction, then you increase the temperature, it'll make K go up. It's just opposite. For the same logical reason. Sometimes we use delta H instead of Q. Delta H is a term which stands for enthalpy. And we don't have time to go into the particulars about the difference between the two. Enthalpy is more of a potential of heat for a reaction, whereas Q is the actual heat transferred during a reaction. The only time that these two are actually equal is when there's no change in pressure. And I don't have time to derive that, but take my word for it. So since Q is measurable and delta H is not, chemists tend to conduct a reaction at constant pressure. Then if they measure Q, they know it's equal to delta H. So that's as far as we can go right now. But when you see a delta H, think of it as heat. It's an energy term. Okay. Other types of conclusions we can draw from the K value. If the K is extremely large, what does that mean? That means that the numerator is big and the denominator is little, which means there's very little reactant left and there's a lot of product produced. So a large K means that products are favored. So flip that around, a small K means that reactants are favored. Okay? Now, there's a distinction between the equilibrium constant and the equilibrium position. Remember when I talked about A, B, and C, D? You're at equilibrium. And if the temperature doesn't change, that K will be constant, no matter what these concentrations are. These concentrations will settle themselves in order to produce equal forward and reverse reactions. And when that happens, then you calculate the K, and it's always constant for a given temperature. But if we add some A, the reaction is going to be, it's going to go that way because we've unbalanced it. And then once the reverse is reestablished, we produce more of these here, we produce more of that. We're going to consume some of that, okay? Once we've reestablished equilibrium, where are the concentrations now? Well, now the C is bigger, the D is bigger, the B is smaller, and the A is bigger because we didn't use all of the A, just some of it. So this new set of concentrations is the equilibrium position. And the equilibrium position can change. It can be different concentrations, but if you take all those new concentrations, you calculate exactly the same K, right? So for a constant temperature, the K is constant, but the equilibrium position is not. Okay? That's an important distinction, actually, especially if we were going to do some calculations. Yeah. But sadly, let's see. Okay, so this came out of your textbook. We talked about very large and very small Ks. If the K is very, very large, you're essentially saying the reaction goes to completion. If the K is close to 1, and because you've got the powers of concentrations in there, you can't actually say 1. I know some textbooks do, but it's not valid. If it's close to 1, in that neighborhood, you can say that you've got concentrations of reactants and products are pretty well balanced. They're not exactly equal, but they're balanced. And then if you've got very, very small, then the reaction essentially doesn't go. So those are things that conclusions you can draw from the K value itself. All right. So how would we write this one? Right. Is it balanced first? 2 hydrogens, 2 iodides, 2 hydrogens, 2 iodides. That's balanced. And we assume that there are no solids and no pure liquids. Which is kind of funny because at room temperature, iodine is a solid and hydrogen is a gas. Let's say the temperature is high enough now so that you've got all gases. How would we write this? Well, you need this one in the numerator, right, with a power of 2. So that's probably it. I don't see any others that are like that. Let's check it. Then you got this one and this one times each other. Yeah, it's D. Okay. Now we've danced around Le Chatelier all the way to this point. Le Chatelier just says that if your system is at equilibrium and you stress it, the system will respond in whatever way required to reestablish equilibrium. It will mitigate the stress. The instructive part is to define what is the stress and to be sure that you have a valid reaction equation to work from. Because if we say, I added this substance, which is part of the reaction, and it moved to the right, that doesn't mean anything unless you have a balanced equation to work from. If you have an equation, then you can say, okay, I added this much of this reactant and it moved to the right based on that equation. Okay, that's perfectly valid. Or you could say, I added hydrogen as the reactant and it produced, and the reaction shifted toward producing more hydrogen iodide. Then that makes sense. But right and left don't mean anything unless you're working from a balanced reaction equation. Okay, so we've talked about changing concentrations already. So if you have, I'm just emphasizing this point again. Let's see. Yeah, I'm beating the dead horse again. If you change concentration, you could do that by adding reactant or adding product, or you can remove reactant or remove product, like the Haber process, where you make ammonia. Well, if you remove ammonia now and you put those gases back in the reaction vessel, they're going to shift toward more ammonia. Because you remove that from their equilibrium state, and now they're going to react some more and reestablish equilibrium. So you can add or subtract reactant or product and disturb the equilibrium. That's one way to disturb the reaction. All right, so that's supposed to be instructive. So what have we done here? This is the equilibrium position for this particular reaction. And then increase the hydrogen. So we add some hydrogen. So what's it going to do? It's going to make more ammonia and consume some of the nitrogen to get there. Okay, we can change the temperature, right? And we've already discussed what does the temperature do to the reaction. Well, it actually changes the K value. But when you're using Le Chatelier, all you need to know is the reaction endothermic or exothermic? If it's endothermic, then the heat term is on the reactant side. If it's exothermic, the heat term is on the product side. Now you can say, if I increase the temperature here, I'm adding heat to this side, it drives the reaction that way. Or this one, if I increase the temperature, it drives the reaction back that way because I added this term. If you're not told whether the reaction is endothermic or exothermic and what would happen with a change in temperature, increase in temperature, for instance, at that point, you either have to say, I don't know, or this is my reasoning. Increased temperature should, well, I don't know. So here we have this reaction, and we know the difference between the two because this species is blue and this one is pink. So if we effective temperature, okay. So we're not told here whether it's exothermic or endothermic. We might be able to deduce it. Let's see if the next slide gives us. No, it doesn't. So if you put the substance in ice and you cool it down, and it loses some blue color. That means it's going this direction. It's going to the right. Right. So we cool it down, make it go this way. So what have we done? Oh, there it is. I'm sorry, I missed it. It's exothermic. So if we cool it down, we're removing some of this, which drives it to the right. Okay. What else can we do to an equilibrium? We can change the pressure. Now, under what circumstances will pressure have an effect? Only if there are gases involved. First condition. Changing pressure. You have to have gases. And you have to have a difference in moles from reactant to product. If you've got gases on both sides of the reaction and you've got the same number of moles of reactant gases as product gases, then changing the pressure will have no effect. Okay, so here we have Haber again, right? Nitrogen, hydrogen, ammonia. So how many moles of gas do you have on the reactant side? You have 3 and 1, it's 4. So you have 4 moles of gas over here. And over here, you have 2 moles. Okay, so if this is at equilibrium, how would you change the pressure? Well, one way, you could add one of these other gases, and that would increase the pressure. But we've already covered that topic, where you add reactants or add products. So we don't need to talk about that one. What if you add an inert gas? That increases the pressure, right? According to Avogadro, you're adding more moles of gas, so it increases the pressure. But what is that? Does that have any influence on the reaction? No, because the added inert gas is not part of the equation. It has no influence at all. You haven't actually increased the concentration or changed the concentration of any of this. So the only way to increase pressure is to change the volume. Well, aside from adding more of each one, we've already covered that. But if you want to keep everything in there at equilibrium and then change the pressure without adding or subtracting, then change the volume. So you decrease the volume, increase the pressure. So how is the system going to react if you increase the pressure? It's going to react to produce fewer moles. You're increasing the pressure, it's going to react by trying to decrease the pressure. And it does that by making fewer moles of gas. So if we increase the pressure, we drive it to the right to make fewer moles. If we decrease the pressure, then it's going to respond to make more moles of gas and go the other direction. So in addition to Haber and his reaction conditions, increasing the temperature, and I'm thinking it's probably 400 or 500 degrees Celsius in this catalyst. He also increased the pressure. So you increase the pressure, you drive the reaction to the right because there are fewer moles of gas on the right than there are on the left. Okay, so we've covered concentration, temperature, pressure. And then there's the catalyst. What effect does the catalyst have on the equilibrium? No effect whatsoever. If you add a catalyst to a reaction, it will change the speed at which you reach equilibrium. But if the system's already at equilibrium and you add a catalyst, it will not change the equilibrium at all. What factors affect the equilibrium reaction according to Le Chatelier? Let's see. Concentrations, yeah. Temperature. And catalyst does not affect. So the one that doesn't have catalyst in it. Not that one, not that one, not that one. This one. C. Catalyst does not affect the equilibrium. Oh, concept, that means we're toward the end. All righty. Let's see, a breathalyzer used to determine the alcohol level of a driver suspected of intoxication. Use the chemical reaction below. Potassium dichromate plus ethanol in the breath plus sulfuric acid yields chromium sulfate. Actually, we have to say chromium. Let's see, 2 minus 3 times 2 minus 6 minus chromium 3 sulfate and potassium sulfate, acetic acid. That's another way to write acetic acid, and water. So in this reaction, something is undergoing reduction to something while something is undergoing oxidation to something. Something is oxidizing agent. Okay, so we need to do oxidation states. All right. Potassiums are all the same on both sides. We don't need to bother with that one. Let's look at chromium here. Let's see, I did this one already. This is +3. This one would be, let's see, -2, -14. This would be +7. Right? Oh, no. I left out potassium. This is +2. So that'd be +6. There we go. So the chromium is going from +6 to +3. So it's being reduced. Chromium actually that is undergoing reduction to while something is undergoing oxidation to something else. Okay, so sulfate's not changing, hydrogen's not changing, potassium's not changing. So we don't have to consider this one or this one. No, that one neither. Sulfate. Okay, so I'm thinking carbon. So we need to find out what is the oxidation state of carbon. All right, so this one's not easy. This one's -2 +1. Hydrogens are +1. So we got 3 pluses. 3, 4, 5, 6. +6 for the hydrogens. We got a -2 for the oxygen. But are these carbons the same? That's the question. If we look at it this way, let's draw it out. Okay. So if this one's -2, that means -1 belongs this way and -1 belongs that way. So we're actually talking about a -1 from this side. This one is a +1, this one's a +1. This one is neutral. So we're saying that +1, +2, -1, that means this carbon has to be a -1. -1, -1, yeah. And this one is +1, +1, +1, and 0. So this carbon has to be a -3. So these two carbons are at different oxidation states. I'm not going to give you one like this. That's too much. But anyway, now when you get to this one, this carbon hasn't changed. It's the same as that one. This carbon, though, this is a -2. This is a +1. That means a -1 is delivered from this side because we have to split it between the two. And this one is a -2, which means that all of this -2 goes to that side. Now this one is +3 because this one's 0. Right? These carbons are essentially equal, so that bond says that there's really no difference between the two. So this one's +3, and over here it was. I said it was -1 here. So -1, the +3 means that carbon was oxidized. So this one is undergoing oxidation. Oops, sorry. CH2OH is undergoing oxidation to this one. Right. What's the oxidizing agent? The oxidizing agent is the one that was reduced. So this is the oxidizing agent. And, oh, excuse me. That's the oxidizing agent. And this is the reducing agent. So let me see if I got it close. Oops. Oh, it's drawing them in for us. So let me get the clutter off of here. And see if I did it the way it's showing up here. So chromium 6+, okay. Chromium 3+, that's right. This one is undergoing oxidation to that one, yes. This is the oxidizing agent, yep. And that's the reducing agent, okay. So that was a difficult one, especially since we really didn't cover what to do with those carbons. But it's not really straightforward. And I didn't give you any rules to go by for the carbons. So it wouldn't be fair to give you one of those on a test. But it's an interesting problem. Oh, that's it. That's it. I guess they figured one of those was enough.